So the first thing is remember how to add fractions. Yeah. And honestly, adding and subtracting is the hardest thing you will ever have to do with fractions. Yeah. So how to actually add these two fractions. And you brought up that what was the key thing that you had to remember when it came to adding these two fractions? What was the concept? Common denominator. So let me throw this question out to everyone else. When do you need a common denominator?
Whenever the numbers are different.
Okay.
Divisive.
Right, so what are the numbers that you're keying in on here? Which numbers? The bottom number.
Oh, yeah.
And which bottom numbers are we looking at here? The 3 and the 4.
Yeah, 3 and 4.
All right. So because those two were different, we had to do something about that before we could add the two fractions. Okay. What about the 7? Why aren't we looking at that?
This is outside.
Outside the parentheses. All right, so why do the parentheses matter? Pemdas. All right, somebody tell me about Pemdas. Yeah, okay, so Pemdas, the order of operations. So Pemdas was the reason that when you look at this expression first, you didn't pay attention to the 6/7 that was out in the front. You first started by completely ignoring that and focusing your attention inside the parentheses. So what Pemdas does for you is it focuses where you're looking. Right? If there are parentheses and you're simplifying an expression, the first place to go is inside those parentheses. If there are multiple sets of parentheses, go inside as far as you can to the innermost set of parentheses and then work your way out. That's the P in Pemdas, and it's why we don't care about the 7 initially. We care first about what's inside the parentheses, simplify everything inside the parentheses as much as possible, then move on to simplifying any exponents. Are there any exponents in this expression? I don't see any. Okay. And then after that, M and D, multiplication and division. Which comes first?
Multiplication. It doesn't matter really, but...
Why not? Why not? Why doesn't it matter, sir?
Because it's the same. Multiplication and division, I just subtract, they're in the same group.
Multiplication and division are in the same, they're in the same group. They're the same operation secretly, right? Anything you can do with division, you can also do with multiplication. If I want to divide by 3, what's that the same as multiplying by? 1/3, exactly. The multiplicative inverse, the reciprocal, right? So every division is just a multiplication in disguise. Every subtraction is an addition in disguise. Right? Which is why in the order of operations, the order of precedence, multiplication and division, neither comes before the other by rule, right? We take them both together and we do them from left to right. Same thing with AS, addition and subtraction. Anything you can do with subtraction, you can do with addition instead. So those two operations are also on the same footing. So that's how you navigate your way through simplifying an expression, is you focus first on what's inside the innermost parentheses, do everything you can inside the parentheses, and when that's all simple, then work your way outwards, starting with exponents, then with multiplication and division, then with addition and subtraction. Okay? Let me back up again to the first question. Common denominators. It's not always necessary to find common denominators for a pair of fractions. When do you need to find common denominators? And when is it okay not to?
When the bottom numbers are different, you need to find it, but when they're the same, you don't have to.
So if I were to change this problem and write 2/3 plus 1/3.
You just go across and solve that, right?
You go across where?
Across
Across what parts? The top. Right. So when the denominators of two fractions are common, they're the same, then I can add those two fractions or subtract those two fractions just by adding or subtracting their numerators. So if that were the problem, 2/3 plus 1/3, we would get 1, exactly, because upstairs we'd get a 3, downstairs we'd get a 3, 3 over 3 can be simplified to 1. So if the denominators were common, we could just add across the numerators. But so far we've focused on the difference between the denominators as being the reason that we need something in common. But I want to go to the next level with this. So common denominator, then add or subtract the numerators. I'm going to hit the pause button on the question I'm trying to ask here, and we'll see it come up a little bit later in this problem. So if we're focusing on 2/3 plus 1/4, how did you carry out that addition? Question?
I brought the denominators to 12 each.
Okay. Why is 12 a good choice?
It seems like the closest or the
Least.
lowest number that each can be multiplied by.
Yeah. 12 is, in fact, the smallest number, which is both a multiple of 3 and also a multiple of 4, right? We call that the least common multiple of the numbers 3 and 4, or LCM if you're being fancy, if you're into the whole brevity thing. So yeah, 12 is a good choice. In fact, what other relationship does 12 have to these denominators?
It's a multiple of each one.
Yeah, exactly. In fact, it is just 3 times 4, right? So that's nice, because that's a shortcut you can always get away with using. If you don't feel like thinking too hard about your common denominators, sometimes I don't like thinking too hard about common denominators, just multiply the denominators. That'll give you a valid common denominator every single time. 3 and 4, it's really the only option, right? But if we had, I don't know, 6 and 4, or, yeah, I guess that's a good version, but I had like 2/6 and 1/4, then we could still use 12 as a common multiple, right? But if we just multiplied across, we'd get something bigger. We'd get 24. So it looks like that choice matters. It doesn't really matter at the end of the day. It just matters how much simplification you end up doing at the end of the problem. But I like multiplying across. That's a handy trick now. It's going to be a really handy trick in Module 9 when we do this kind of arithmetic, but with variables cluttering up the screen. Okay, so we've decided 12 is a good common denominator. What do you do after that? Now that we've decided we want the 12s, what else do we do?
You have to multiply 4 times 2.
Okay.
So that's going to multiply it 3 times. And then with 1 times 3, so you get.
Whatever you do to the top, you gotta do to the bottom.
There we go. So that's thinking like a mathematician right there, right? So that's the general principle behind how we change fractions without changing their value. How do we change the numbers we use to represent a rational number without changing the value of that rational number? Well, the principle is whatever we multiply one of the parts of the fraction by, we also have to multiply the other part by. It's the same as in saying if I have a big pool of money and I want to distribute it to a bunch of people. Like we have 16, let's say 16, I'm going to round it. 16 of you, and I have up here, $80 to give away. Well, that's great. That means each of you gets $5 if I'm being fair, right? But if I double the amount of money that I have up in the front, now you all are going to get twice as much. But if I bring in twice as many people, now you're all back down to the 5 again, right? So if I double the amount that I have to give away and I double the number of people I'm giving it to, everybody still gets the same amount as they did before. That's what I like to call the principle of balance. Whatever you multiply one part of the fraction by, you also have to multiply the other part of the fraction by. And I have a typo on the board. My apologies. Times 3. Yeah. I've heard of professors giving away like quarters to people who catch their typos in class. I would quickly go broke, so I don't do that. Okay. So we decided we need to multiply both parts of the first fraction by 4 because 4 is indeed what you multiplied 3 by to get 12. So whatever we did to the bottom, we also have to do to the top 2 times 4. Ditto on the right side. Because to turn a 4 into a 12, we multiplied by 3. We also multiply the numerator by 3. And end up with 8 plus 3. This is what everybody had inside the parentheses up until this point?
Yeah.
Great. So the common denominator is there. And now that the denominator is common, what do we do?
Just add them.
Add across them being the numerators, right? So 8 plus 3. So inside of the fraction, inside of the parentheses, you ended up with the fraction, oops, try and use a color we can read, 11 over 12. Okay, so far so good. We got through the addition of fractions part, which is anytime you're doing fraction addition, it's the hardest thing you're going to do with fractions in that problem. And that also means we've done all the arithmetic inside the parentheses, which means we're ready to widen our perspective and also look at what was outside the parentheses. So if I carry that down, What do I have to do next?
Multiply it times the 6 over 7.
Yeah, so now I have a fraction multiplication problem to do. All right, so how do you multiply two fractions?
She told me go across.
Ah, go across. Okay, so did anybody have a different, did anybody try something else besides multiplying across?
Initially, I probably would have tried to cross multiply.
Anyone else do that? Don't be shy.
Yeah.
Yeah. No, we see this every day in math services, like, oh, cross multiply, because this idea of cross multiplying gets beaten into people's heads somewhere along the line. It's not cross multiplying, it's multiplying across, right? Stick that in your pipe and smoke it. Yeah. So cross multiplication is good for a lot of things. In fact, we secretly already did a cross multiplication in this problem. I didn't highlight it, but if you multiply your denominators 3 and 4 to get 12, right, to get our common denominator, it turns out that where did our 8 and our 3 come from over here? The 8 was 2 times 4, the 3 was 3 times 1. Those were the cross products of our original fraction. If you just take a look, that was this product, 2 times 4 gave me that 8, and then this product, 3 times 1, gave me the 3 for over here. So cross multiplication has its place, but it doesn't do what people think it does. It's not a one-size-fits-all trick. Multiply fractions by multiplying across the numerator and denominator. All right, and before I do that, though, what about, because our denominators aren't common here. We have a denominator of 12, a denominator of 7. What's the deal?
Still go across.
Still go across?
I see, I don't even know if this is right, but I just multiplied everything times 4. So you get a common denominator of 48, and then went from there.
Common denominator of 48, except that 48 is not a multiple of 7. 49 is a multiple of 7. See, these are the little 2-digit arithmetic things that are, if something trips you up in arithmetic, it's going to be that, or it's going to be negative signs. Those are going to be your not friends for the remainder of the semester. So we could try to scale these up to a common denominator.
7 times 4 is 28.
7 times 4 is 28, but then if one of the fractions, if one of these fractions, yeah. So here's the thing. We could put these two fractions into common denominators to give you a sense of what that would look like. Since 12 and 7 actually don't have any common factors, there's nothing that goes into both 12 and 7 other than 1, we would have to go all the way up by multiplying 12 times 7 to get 84. And then we would have to multiply two fractions whose denominators were 84, 72 over 84 and 77. And so I'd have to multiply 77 times 72, and then 84 times 84. And yeah, I have a PhD in mathematics, and I'm not that great at this 2-digit arithmetic on my feet. Let's see. So that's 11 times 7 times 72. So that's 792 times 7. Oh gosh, 5,500. You know what? I'm not even going to take a guess at this. Big numbers. Big numbers over big numbers that you probably don't want to have to deal with on a quiz or on an exam or something, right? So what's the good news? We don't have to. We don't need common denominators when we're what? Multiplying. Which also means we don't need them when we're dividing. Right, exactly. So that's the really great news about multiplying and dividing fractions is that they can come as they are. No common denominator needed. It's not wrong to do it. It just makes your life a little bit more miserable, right? Denominators needed. Lost the tune there for a second. Okay, so no common denominator is needed for multiplying or dividing fractions. So we can just go directly across. 11 times 6, 66. 12 times 7, 84. Okay. So now we've gotten to the end of the Pemdas train, and we have a fraction 66 over 84. What comes next?
You gotta
Simplify. Alex is nice enough to actually tell you, write your answer in simplest form. Our quizzes, our exams are all taken with language directly from the questions in Alex. So I'm not gonna come at these problems any differently. It'll say, write your answer in simplest form. So how do we do that? How do we reduce 66 over 84 into a simpler form?
I like to just divide by whatever number can go into both.
Exactly. Divide by whatever number goes into both 66 and 84, because whatever we divide one by, we have to divide the other by. The trick is finding something that divides both, right? So what number goes into both 66 and 84? Yeah. And you can do this. 6 is also correct. But 6 can't go into something unless 2 also goes into it, right? So you can start as small as you like, just starting with 2's, or you can look for bigger chunks and try and knock off bigger chunks at a time. That's up to you. Taking a bunch of little steps is sometimes easier than trying to take one big one. So if I divide by 2's, divide by 2, that looks like a plus. Divide by 2. I'll get 33 over 42. Okay, but now I'm at 33 over 42, and am I done? How do I know I'm not done? We can still go lower, but we can't get any more mileage out of 2's, right? We can't divide 2, because 2 doesn't go into 33. So what do I have to divide by this time? 3. Luckily, 3 does go into 33 and 42. 3 into 42 is, what did you get here? 14. There we go. And from there, 11 over 14?
That's good.
That's it. That's done. 11 is what kind of a number? It's an odd number, but it's better than an odd number. It's a prime number, right. It's not divisible by anything except for itself and for 1. And so at that point, because itself, 11, doesn't go into 14, and 1 doesn't help us, we're done. No common factors on top and bottom. We get to stop. So Tim's point was about 6. We could have divided by 6 from the beginning and taken one step in this process. Divide by 6. But that's really just the same thing as dividing by 2 and then dividing by 3. So whichever way you prefer to do it, you will end up at the same answer.